thanks everybody for the last class. That one was a bit shorter, and now I'm very stressed out about this class because this one is supposed to cover a lot of topics, okay? So I'm very stressed out because I have to finish, otherwise it would be very difficult for others to carry on. So at some points, at some parts, I may just go through very fast. Anyway, so if you find it difficult, just stop me and ask, okay? Because I'm stressed out, so maybe some parts would be very fast. Okay, so for sure, we will have a break. Let's try to make that break at about 2:45, okay? Or let's say 2:50, because we have this visiting students coming in at about 3 p.m. So we can have that break at around that time. So we can have, let's say, about 20 minutes or so. So now it's 1:25, so we can carry on for 1 hour, 1.5 hours, and then we should be back after 20 minutes of break. So thanks for the last class, because I don't really like to carry on long without any break. But okay, all of you agreed, so we could do it. Okay, so for today's class, we're gonna go over classification. So which is basically, as we discussed last class, going over categorical data. And then the big topic is how to think about deep neural net. Okay. So with that, let's begin. So we must have a review of last class. So last class was essentially focusing on regression task. So the point here is that output variables are always continuous, right? So we are predicting mileage of a car, and it could be any numbers, okay? Continuous numbers. Then we thought about going from a single variable to multivariable integration. And this we can think of some form of mapping. And if we think about this as some form of mapping, so for a single variable, it's a map of real numbers going from one point to another point. And for multivariable, that small n is basically thinking about many features in the data. So when I say multivariable linear integration, you think about this as data that contains many features. So the small n will always, if not otherwise mentioned, will always denote features in your data. So we had this both, and when we think about it's a mapping, basically then machine learning boils down to finding out this mapping function. So that was the main point. We mostly focused on linear regression. So we had some linear function assumption, and then we went from linear function, from just a simple equation of line, we went to matrices, to think about data as matrices, and then we think about finding these parameters as some form of operators that operate on the data matrix. Very cool way to think. And I think it's a cool way to think because this kind of works for all types of data. Then we thought about the loss function. How do we think about loss function for regression? And it's essentially boiled down to finding out how the residual looks like. Then, after all of this, we went through mean squared error, minimal absolute error, and then we went to emphasize again that machine learning problem is better to think about this as some form of optimization problem. So now we're going to go to a different type of optimization, which is what do we do when we have categorical data? So categorical data is discontinuous. So we have only 0 and 1 as my output. So let's say I have this very simple data set, given the number of study hours, whether a student will pass or fail. So I can just plot it down, right? Given the number of study hours, whether the student will pass or fail, and I have only 0 and 1 as my output variable. So let's say I put another number in between. So the idea of the model is that, let's say, I don't know, let's say some student studied 11.5 hours. Now I have to make a guess whether that student will pass or fail. So that's the idea. So in this case, the output variable now is limited to only 0 and 1. Okay? So we started from continuous space. So you see this R is the input. So input is mapped to only discrete variables, 0 and 1. This is very different from mapping it to another continuous variable. This is for regression. This is for classification, for categorical data. So now we have to think like, how can we proceed when my output is discrete between 0 and 1? So this is the big difference going from regression to classification. Next, I think it's better we build on things that we do know. So what we do know is that regression works for continuous data. So let's try to build from there. So if we have our regression model, basically a simple line equation, y is equals to mx plus c, in this case, weights and bias. So we can start from there. And in this case, we know that the output variable can be any number. So it's basically from minus infinity to plus infinity, any number. It's a continuous variable. It can be any number. So we can start from here. Our idea is to somehow transfer this from continuous data space to a discrete data space. Luckily, there is a function that does it. So let's see that cool function, okay? That cool function is very famous in mathematics and in population modeling. That function is called sigmoid function. So the sigmoid within Z, so Z is the independent variable. It models as on the denominator as a minus of the exponent, okay? When I put the Z, so I take Z is Wx plus B, okay? So when I put the Z here, now the job of that function basically is to squeeze from plus minus infinity to 0 and 1. A super cool function. So how does it look like? So let's plot this, okay? You will see the code on the web page. Just a simple one-line code. So we take some numbers, and I have my z. So z is basically wx plus b. So I can have different w. So the plot is actually shown for different values of w. And what you see here is that one thing to verify is that, let's say, when the w is getting close to 0. So when w is getting close to 0, so this z is basically, so in here, I don't have any bias. It's only the slope term. So when the w is getting close to 0, so z is getting close to 0. At that point, what I have is something like 1 over 1 plus 1. So basically half. So test this, that when I put w equals to 0, this should be a constant line at 0.5. For other values of w, it looks pretty interesting because now I could actually model the data. But we also verified that putting that linear form on that denominator of the exponent, which is the job of the sigmoid function, it essentially transforms what I intended it to be. So it goes from minus infinity to plus infinity from a regression problem. Now the output is limited between 0 and 1. So now the output is limited between 0 and 1, but it's not discrete. It could be, you see in the plot, it could be any number between 0 and 1. So it is still continuous. So how do I make it to a discrete number? This is a very important point in classification task. What we do is we make a threshold, okay? So the threshold is actually choice. How do we choose the threshold? You will learn later in the data processing class. So let's say we can make a simple threshold choice. When this probability value, when this value, whatever is plotted here, is above 0.5, above half, I set the threshold as 1. When it's below 0.5, I set it as 0. So now, first, so basically two steps happen. Regression, then I put it on the sigmoid function that basically make the output variables between 0 and 1. Then, from continuous numbers between 0 and 1, I put a threshold that will make the output between only 0 and 1, okay? No in-between value. So any number between this, I have many numbers in between, right? 0.7, 0.752, 0.342, blah, 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 etc., etc. But the moment I make this cut, so let's say I have a number 0.342, okay? A continuous number. Then I make this cut. So 0.342 is less than 0.5. Great. So that means my output is now 0. So the whole problem can be thought of again as finding out the possibility or the likelihood of explaining the data. One more time. You can always think about optimization problem as some sort of posterior or likelihood estimation. In this case, we're trying to explain the data Y given X. X is our data and Y is output. So the features of the data, the number of samples, all are within X. And we are trying to predict Y. In this case, Y is basically whether the student will pass or fail. And that is modeled over the sigmoid function. And the independent term within the sigmoid, the Z is essentially the linear function. Okay, so from here, we can think about how do we proceed to develop a loss function. So before we go to loss function, first is that sigmoid is very smooth. It's a continuous function and it's differentiable at all points. The other part also, sigmoid is very cool because it appears a lot, Sanya knows, because we taught this in bachelor's first year. So it's the first part of the population growth. So if you remember the COVID curve, it was something like this. The viral infection went up. That going up is basically given by a sigmoid curve, and then it goes down. The very common population growth. It's like you keep a large amount of penguin in an island. It will grow like this. The number of penguins will saturate. Okay. So that's basically the sigmoid curve. It's also a solution of a nonlinear differential equation. Okay? Then, how do we now choose the loss? What does it mean to have a loss in this case? Because now the output variable is essentially some numbers between 0 and 1, and then I make a threshold to have only 0 and 1. Okay, so how do I choose the loss function? Now, in this case, we can think about, let's say, going with what we know. So we start off with the loss function mean squared error. Okay, so mean squared error. So we have Y as my ground truth, and then this is from prediction. Okay, and then I take a square. I can have a sum over all the samples. So once I do this, I have to think about the derivative. So this is loss. This loss is related to this Y hat. Okay, because that's the thing I'm trying to predict. The Y hat, the prediction is related to W, the weight parameter. If you look back one more time, we started from regression. There, that's the thing we are actually trying to optimize. What is the value of W? You look at this curve. This curve only varies according to different values of W. So we are trying to optimize the weight parameter. So we've got to take a derivative with respect to W. So let's start with mean squared error, okay? What is this? Oh, now we have a big trouble because we have something like this. What the hell is this? So we started from here, and then on the slide it's written that, oh my God, what is this? So Y minus Y hat, then what is this? Sigma dash, I don't know what is this. What is sigma dash? So I have something like this, okay? How do I come to this? To go back to bachelor's first year one more time again. This actually comes from a chain rule, okay? So we started from here. We have to show that the derivative with respect to W looks something like this. How do I think about taking a derivative with respect to W? Because on this line, if I look at the right-hand side of the equation, there is no W. So this is the starting point of chain root. What I see on the right-hand side is a derivative. I can take a derivative with respect to Y hat. So the way I think is I start off with something like this, del Y dash. Now, this Y dash, where does this Y dash come from? This Y dash is essentially related to that sigmoid function, okay? So Y dash is sigma of Z. And this Z was my linear variable, WTX plus B. So I have to go step by step. That's the idea of the chain. First, I take a derivative with respect to y hat. Then I'm going to go derivative of y hat with respect to z, because that's the connection between y and z. Then z is connected to w. So if I take a derivative of this, the 2 will come out. Okay. Then I have y minus y hat del y dash of del z. That's basically this function derivative. That's the derivative of sigmoid. Okay. And then finally this one, del z del w. That's essentially just the x. Okay. So that's the answer. That's how it works. This is just to review because this will come again in the later part of the classes. Don't get confused because you have to somehow find the connection from here to the variable with what I am taking the derivative. So after I put all of this, and there's another thing that you need to know, just try it at home, 5 minutes derivative. The derivative of sigma is sigma times 1 minus sigma. And sigma is essentially y hat. So this is y hat times 1 minus y hat. That's what is written on the slide, I hope. I hope I didn't make a mistake. Okay, good. I didn't make a mistake. So that's what is the final output. So we stop here, okay? We stop here because from now on here, you will not understand much thing. But I make a statement, and hopefully the statement will be clear later on. But let's try to see the statement is true or not. We will try to understand the statement later part in the class. So what I'm saying is that, so let's say when the predicted output is close to 0 or 1, you can take any number. So predicted output is y hat. So if let's say the predicted output is 0, okay? So let's say if it is 0, this derivative is pretty close to 0. So why is that a problem? So let's see why that could be a problem. Let's just keep that in the back of our mind. So we had something like this, del L, del W. It turned out to be, we had y hat, 1 minus y hat. Then we had a y at some point. Yes, y minus y hat, and then x. So let's say my ground truth is 1. But my prediction is 0. This is a terrible prediction, okay? So the student is supposed to pass, but I say that the student will fail. Poor student, okay? He or she will cry. So I don't want this. But what's happening here? So let's try to put this. So y hat. So y hat is 0. Okay. So 1 minus 0 times this y is 1. 1 minus 0 times x. Now you see that it doesn't matter what the x is. This is very close to 0. So the gradient is very small. But, go. Yes. Exactly. No, but the good point. Good point. Why I said it's close to 0? Because I still haven't made the cut on the threshold. So it's still predicting some continuous numbers. So let's say the prediction is something like 0.001. So when I make a cut on the prediction, then it will be 0. I'm just working with the raw value. So now I have terrible prediction, but my gradient is basically 0. Okay, keep that in mind. The statement is, this is a terrible idea. I don't want this. Okay, when my error is very high, I want my gradient to be very high. Why? That will be clear later on. So this loss is not a good idea. Now, from the book I copy that I have another loss. That loss is, oh my God, this is a terrible loss. This is called a cross entropy loss. So cross entropy loss is relating again true and prediction, but via a logarithmic term. So I have something like y high, so ground truth. Then it's related to the prediction over a log. And then for the other term, so 1 minus y and log 1. Okay? Then another term with the 1 minus y. So I'm saying that this loss is better. So this will be a homework later on for the PhD students, okay? But let's now try to establish some other stuff that just appears from the loss itself, is that it doesn't matter whatever the output variable is, okay? Whatever y hat is. So I have the other one, 1 minus y, and 1 minus y I hat. This, because of the minus sign at the forefront, the loss will be always positive. You can try different numbers. This loss will always be positive. This has some implications later on. If I get time, I'll come back to this. This is the homework for the PhD student. Okay? Just try. Just try to apply the chain rule. Instead of the mean squared error, you're going to try the chain rule on the log loss, loss entropy loss, or also called the log loss. You're going to apply this on this loss. Then you're going to see something very interesting. Now, the gradient is somehow will be proportional to the difference. Okay? Verify this. The gradient is now proportional to the difference. According to me, this is better. Okay? You will understand why this is better because we have some nice animation later on. So this is the loss for classification. How do I think about this loss? Because we spent so much time on last class thinking about mean squared error. Yeah, this will be clear later on. So if you didn't understand no math, what the hell is this log doing? What is this chain rule? You don't need to understand, I guess. Even though I don't agree, I guess, okay? If there is time, I will make another comment on this. The thing is that you don't need to understand because look at this. Last time we showed that the regression was basically 5-line pool. You just need to remember for regression, we can apply mean squared error. And when I compile the model, I can just call mean underscore squared error. You don't need to give a shit about residual. You don't need to care about what's going on. How did it come to mean squared error? You just call it and it will work. Same thing happens when you have classification. You just call binary cross entropy. You don't need to know nothing, okay? This will work. Unbelievably, this will work, okay? So all of this you can forget, whatever math, this will work. But I still recommend that you go through the math so that it's a bit more clear. It's super easy. That's why Python can be sometimes problematic because of all the libraries. You remember the XKCD meme? We had this import anti-gravity, okay? We have no clue what is gravity or anti-gravity, but we can import it. So we can import the loss like that. We may have no clue, may not have any clue, but it will work. Okay, so how do I think about this loss? Is there a way that I can justify that this loss actually makes sense for a classification data? So I think about this loss as a modeling of a data where my output can be thought of as a series of yes and no questions. So let's say given a data, okay, the number of hours the student studied. And then I'm gonna ask whether the student will pass or not. So this will be a series of yes and no questions. This back when I was preparing for job interviews 2018-19, this was a very common question at the very first round. So in the company, when you interview, it's like 3 or 4 rounds for machine learning researchers. This types of question will appear in the first round from the recruiter itself, okay? So this is a coin toss problem. So let's say now the recruiter asked you, okay, given an array of 50 coin toss, IID is independent and identically distributed. That means if I toss the coin, one coin toss result is independent of the other. So they are not correlated. So they are independent and identically distributed. So all the coin tosses are happening in the same room under the same condition, and they are completely uncorrelated. So that's this IID. So you have this 50 coin tosses, and then let's say I'm given an array, head and tail and blah, blah, blah. Okay. Now the question from the interviewer is, tell me, what's the possibility that this coin is biased and it has a probability of head instead of 0.5, it has a probability of 0.4. How do I solve this problem? Yeah. How do I solve it? Any answers from the students? Now you're in a job interview. Yeah. You will get no job, no money, but try to think. What's the answer for this? How do I think about this? So you have to write a mini program. First, you have to explain to the recruiter how does it work, and you have to write a mini program. The explanation of this is I have to think in terms of something called the Bernoulli distribution. Okay? Coin toss problem. Never forget, coin toss is related with Bernoulli distribution. I have only two outputs, 0 and 1. So now I have this modeling equation. So P is, let's say, the probability of head, and N is the number of times head appear. So I'm going to count how many times 1 appear. If 1 is head, that would be 0.4 times number of heads, and 1 minus P is 0.6 times number of tails. I guess you have already guessed this, that a log of this would result into something like this: n log P plus m log 1 minus P. This is insanely similar to the cross entropy loss. And that's where the cross entropy loss is actually coming from. How similar is this? The N and M, these are total number of toss. So let's say I have 100 toss. Total number is K. If I divide by 100, basically normalize over the whole data, this is essentially 1. So if I think of this as an n log P plus, I can think about 1 minus n log 1 minus P. This now looks even more similar to the cross entropy loss. That's the idea. When I have my output variable chosen between 0 and 1, the best way to think about the loss, or in general, the data distribution, as some form of Bernoulli output. Very cool. Okay? Super cool. Here, we are not thinking about the residual. We are thinking about the data itself. Okay? So I have some output. I'm thinking about where this output can come from. I think about this output as a series of yes and no questions, because that's classification. Whether this image is dog or not a dog, yes or no. This can be modeled as Bernoulli distribution. Next on, what if I have more than 2 classes? So let's say given some, you go to some Netflix, you have to do some natural language processing. So you download all the reviews, and from the reviews, you have to make a judgment. Given a new review, you have to, sorry. Given a new review, whether, sorry. Given a new review, what's the type of the movie it is? Is it a horror movie? Is it a science fiction? And blah, blah, blah. So now instead of 2 classes, so let's say pass or fail, I have many classes. How do I think about this? So before I was predicting output only as 0 and 1, but now I have more than 2 classes. So in this case, the way I think, I will try to predict a score for every class. So let's say I'm gonna predict this is 10% horror movie. After I read the review, 50% science fiction, and blah, 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 whatever other classes are. They should all sum up to 1, okay? Instead of sigmoid, now think about this as softmax function. One more time, no, you actually don't need to know this. You could just call softmax and it will appear on the Python, but it's better to think that how it actually works. So softmax is, I try to predict the class for 1 and then sum over all other classes. Okay, so this is running for all classes. I have k number of classes. Let's say 4 different types of movies that I'm trying to predict. How does this thing work? let's try to go step by step. Not difficult. So we're going to apply the linear transformation for every class. Okay. Then we're going to gather up the score. So we will get this Z for all classes. We have K number of classes. Let's say 4 or 5 different movies. Then we will try to calculate the sigma or the softmax for every class. So let's say for the first one. So for the first one, the Z value is 0.34. So 0.34 goes on the exponent, and then I sum up everything else. So this, the denominator, you can think of something like a normalization. And then I get all the values of this P1. So I'm going to have an array of P1, P2, P3. So let's say if I have only three classes. From then on, so let's say for the first one, I have some number, I don't know, 0.2. Then for the P2, I have 0.45. So this is 0.65. Then for the last one, it has to be 0.35. So from this one, I know that the movie is class 2. I don't know. Let's say this is a horror movie. Okay? The way this works in a Python is just one line. I just take the argument of the maximum. So the maximum is this. Argument is class 2, 1, 2, and 3. And that's it. Goes with the same principle. Just the function is different. Instead of just some number between 0 and 1, now I have a softmax. When I add the probabilities, they should be equal, not this. When I add the probabilities for sigma, all of this here, the P1, P2, P3, they should be 1. That's it. Now, how do I think about the loss function for this one? Because now I have, instead of 2 classes, I have 3 classes, 5 classes, 10 classes. Okay? For 2 classes, I had binary cross entropy. For multiple classes, I have categorical cross entropy. Look, it's essentially not having the second term. You can think about the second term on that binary cross entropy as a negation. So let's say I have I have 0.4% of possibility of head. Then the remaining 0.6 is already tail. That's why I have that. You can think of like that the binary cross entropy, I have this 1 minus y term. For categorical, I don't need it. The softmax does the job of this remaining summation that should go to 1. That happens on the denominator. Very cool way to think. But how do I now justify this loss function? First, let's see, how does this work? So let's say given a set of images, I know the true label. So the true label in this case is supplied as an array. So let's say this is a dog. So I have cat, dog, and rabbit. So the true label is given for dog, that this image belongs to a dog, okay? Or this image represents a dog. Then I get these predicted probabilities. Of course, I see that my probability prediction is right because it's the highest for the dog. Then I calculate the loss, okay? I calculate the loss individually for every class. Look at this summation. This is actually going for every class. And then I do it for the whole data set. But I go first class by class and then for the whole data set. Once I have this, I guess you understood, just like binary cross entropy, because of the negative term in front, categorical cross entropy is also always positive. Okay? So now where does this thing come from? If that one comes from binomial distribution, where does this loss come from? This one is actually not so used as much. This one comes from a categorical distribution. So I take the likelihood of the categorical distribution, and then I essentially have categorical cross entropy loss. Okay, we use the binomial distribution a lot. This one you essentially think of as like a multinomial distribution. Then I take a likelihood and I have my categorical cross entropy loss. Okay, the labels are usually one hot encoded. That's what it means, this one hot encoded. You will see in the notebook. If we have time, we can go through the notebook. What does it mean in more detail? But one hot encoded is, I have multiple classes. The one that is hot, or actually truth, that flag is raised to 1. Everything else is 0. Then I'm going to predict a series of probabilities. And then I'm going to choose numpy argmax of this. Maximum is this, argument of this is 1. So that is done. Okay. You don't need to know nothing because look at this. Now I have categorical cross entropy. So you can forget what happened in past 1.5 or 2 hours. You just remember these 3 blocks of codes, okay? Think about your data and then you compile a model. You will see what a model is and then you could just use your loss. You can forget. A lot of machine learning works like this. You no need to know nothing, it just works, okay? A mini interval. So what we have done so far is we set up the conditions for thinking about regression and classification, continuous data and categorical data. We thought about loss functions. What we didn't discuss is this very important point. This gradient descent and the loss was proportional to the output misclassification, blah, blah. What is this? That will come soon. The other thing that is not discussed, different types of algorithms. You will have many different classification algorithms, okay? One of my favorite is support vector machine, not discussed. The other one that works very well is called boosted decision tree, basically a form of decision tree, not discussed because there is no time. But at least you know the fundamentals. How do I think about a regression problem? How do I think about classification problem? Now you can go on ChatGPT, upload your data, and ask ChatGPT, give me a series of classification algorithms so that I can compare. Okay? Then you can compare which one is good. So let's say you're writing the project like this. You just uploaded your data on ChatGPT and you get something. Okay? You have to be very shrewd in your justification. Why this works for your data and why this doesn't work for, or why it didn't work for the other algorithm, why it did work for this algorithm. You have to justify. Okay? But that you need to dig a little bit deeper. Yeah, it's a mini interval and the dog is little, okay? So that's, I think, the joke is. I don't know what happened to the tail. This is a very weird thing, okay? Poor dog, okay. Another important task. When you deal with data, it's a very common question that will appear in the referee report. What about the feature correlation in your data? Did you actually study how different features are correlated? So we're going to go over a very cool algorithm. Because we discussed matrices in so detail, we should be able to understand how PCA actually works. And something fundamental will come out of this. Okay, so let's see. So let's say we are given this data, something like length and diameter. Okay, so I try to plot this and I see that there is a very strong correlation between the length and the diameter. So this abalone data, I will upload this on the GitHub webpage. This is like a mollusk. This is like a shell. So you take data points of the shell length and the shell diameter, and then I see a very strong correlation. At this point, I definitely, if I build an algorithm, and if the referee asks, okay, why do you need these 2 features separately? I don't need these 2 features because they are very strongly correlated. I can have only one of them. So how do I proceed with this kind of problems, okay? So I usually try to calculate something called the covariance matrix. So you remember how we define the data matrix? It's something like R, I have n samples and n features. I then try to calculate the covariance matrix, which will give me a matrix of features, the covariance of the features. Okay? That's why it's n times n, because it's now dealing with the feature space. The diagonal term of this matrix, the diagonal terms x11, x22, these are basically your variances, and all other terms, x21, x12, these are covariances, basically how the features are correlated. So we need to calculate that. If most of the things are lying on the diagonal, then we know that the features are almost independent. If not, then the features are correlated. We have to think a bit more detail. The idea of the PCA is basically along which direction the data has the maximal variance. What does that mean? So we have this feature covariance matrix. We're trying to find a direction along which the data has the maximum variance. So let's say I had these two features. The covariance is neither along this direction, but the covariance maximal is along the diagonal direction. So the PCA's job is to find that direction. So somehow I need to find that diagonal axis. Okay? So that's essentially the task is. How do I do this? This is a very simple algorithm. So let's try to go step by step. Very short, but very, very, very cool algorithm. So after I have this feature covariance matrix, what I do is I try to reduce the dimension because that's my final goal. So I have n features. I would like to have k features, which is hopefully less than the initial number of features. Okay. So then basically this becomes like finding two directions or three directions. So let's say you have 5 features. You want to have little less features because you see the correlation plot and you have something like this. Okay. So I want to find minimal axis where one of the axes represents maximal variation and the other is perpendicular, very less variation. Okay. You can think about this basically as rotating the coordinate system. So the way we proceed, this was another very common interview question, okay? So you have to explain, this is a second round interview. So you have to explain the PCA algorithm. You start off with a generic matrix, some matrix, you define your own matrix, a 2D matrix, and then you have to go through the algorithm step by step during the interview, 20 minutes interview round, okay? So how does it work? So we calculate the feature-wise mean. Okay, so let's see an example and then we subtract the mean. So let's say I have a data set with 3 samples and 2 features. Okay, so feature wise mean is I have 3 samples. So this is the first feature. So let's say 3 plus 1 plus 2, that's 6, 4, 3, 7 to 9, 9.6. I divide by the number of samples, that is 3.2. That's the feature wise mean. After I calculate the feature wise mean, I subtract it. Now, once I have this subtraction, this is after the subtraction, okay? The subtraction of the mean. So now the data is centered around, this feature matrix is centered around the mean. Then I calculate the covariance. Now, initially I had 3 by 2, 2 features. So the covariance matrix would be 2 by 2. Okay. This should be now very obvious as we are proceeding. Okay, so what we see here, let's say for particularly this case, we have some number 0.61, which is a relatively strong number. So let's say in this case, we have a reasonable strong correlation. At this point, the final step is trying to find the eigenvalue and eigenvector of this matrix. Okay. If you remember the eigenvalue equation, it was something like this. I have a matrix A. If this is the eigenvector, then this should satisfy the eigenvalue equation. This is some scalar number. Matrix operating on a vector gives the same vector. So the vector didn't change direction. This is just a scalar number. Let's see some animation. How does that look like? Once we have the eigenvalue and eigenvector, I find the maximum eigenvalue and the corresponding eigenvector, and I project the data. Projecting the data is just simply taking a dot product along that direction, okay? This is the PCA direction with the maximum eigenvalue. So let's see, how does that look like? Why eigenvalue is so cool? There's a nice animation. So you remember this one from the last class. So let's try to see a GIF of this. How does it look like? So let's say we have this matrix that looks similar to this shear matrix. And then we apply it on the 1, 0 and 0, 1. What is 1, 0 and 0, 1? They are basically my X and Y axis. This is 1, 0 and this is 0, 1. Okay. So I know that my axis now will be shear. So let's see how does that look like. So we started from a unit square, apply that matrix. Now it looks like this. Okay. So now let's think about taking a vector. Okay. Let's take a vector. I don't know. Let's say 1, 1 along that direction. Okay, so I take a vector 1, 1 along the diagonal of the original unit square. If I apply this matrix, I actually don't get back the same vector. The vector has changed. So immediately I know that this is not an eigenvector. What is an eigenvector? For this one, I know the solution because I calculated. So it's -1 and 1. So instead of this direction, if it is along this direction, -1, 1, 1, you see that I apply the matrix on this vector and the direction remains the same. It just got scaled. It was initially 1 unit, now it got scaled. Now, because this is a direction, I also immediately know that if I extend this, this should be 1 minus 1. That's another eigenvector direction. How does that look like? I initially had 1 minus 1, I sheared it, and I still have the same direction. That's the job of eigenvalue and eigenvector. What's happened here? I tried to find the maximum variance of the data and then look back to find in which directions these eigenvectors are still constant. I mean, that's why they are called eigenvectors. We are trying to find those directions. So what happened? Subtract the mean from the feature matrix, calculate the covariance, then find the eigenvalue and eigenvector. Super cool concept. Why they're so cool? So let's just go over how do we apply this. Last 5 minutes before we take a break. Okay, so let's say we are given this breast cancer data set. Okay, so these are basically images, and then we make some measurement on the tumor, and we have to predict whether this is a malign or a benign or a malignant case. Okay, so the table looks something like this. You will see on the node. So we have many features, many features. Okay. So you see the features look something like this. So let's say the radius of the tumor, the texture of the tumor, perimeter, area, blah, blah, blah. Just by looking at those features, you should already guess that the radius of the tumor should be correlated with the area or the perimeter. So we can verify this. Okay. Area and the radius are pretty correlated. So maybe it's not useful enough to use both of these features to do some classification. I can plot the correlation matrix that looks something like this. So let's say if I go to mean radius is extremely correlated with mean perimeter, okay? That should make sense. And you can check through the other parts. They should make sense too. How do I apply PCA? You forget about all the algorithm, you just call PCA. Okay? Unbelievable. It's quite unbelievable that Python is like this, okay? So you don't need to know nothing, you just call PCA and it will work. So I have 4 principal components. So what has happened here? I had a data set of, let's say, 30 or 40 features. Now I'm trying to find the 4 principal directions where I have maximal amount of variance, okay? And then I try to plot the test data along these 2 components. Oh my God, they look like this, okay? It's crap. It's like a gray plot. What am I supposed to do with this plot? What does it mean? So then I hire a PhD student for free, because nobody pays PhD student. So we hire a PhD student for free, and then I ask the PhD student to look back for these data points, the corresponding patient ID, and then mark these dots with the colors, whether they are malignant or benign. Okay? No PhD students were harmed. Okay, that was a joke. Then it looks very cool. Then I see a clear separation between malignant and benign case. Just a simple linear transformation gives me the classification. What a cool thing to have. Damn, super cool. So think about your data. If you have some correlation or not, this is a simple way to reduce your correlation. This is just simple linear operation. There are some nonlinear mapping, something like a TSNE, UMAP, but this one is so easy to understand and so common in interviews. It's better to know at least what's happening with PCA step by step. So what's the time? Let's try to take a break. 2:13? Yeah. So I think we can start at, let's say, 30. I think we can start at 2:30. Let's just see what's in the next section. What is in the next section? I think we can go to neural nets. Oh, this one is too long. So afraid this will take too long.
But okay, so I mean, I think it's okay to take a bit more time, but to explain things properly. But will you meet in the same room, or you will move to the computer room for the next
No,
part?
Gabby. So now let's say it's about 2:30. What was it?
Sorry?
Okay, so let's do it like this, the way we planned. So let's do it like this. We continue till 2:40 or 2:45, and then
And
we take a
then?
break to see whether the students will come here or how many. If this is one, he or she can just sit with us. If this is 10, then we have to leave. Okay. So let's just continue. Okay. Is this okay for everybody if we continue? So that we take that break, that 20 minutes or 15 minutes break at about 2:40, 2:45 to see how many students are there.
Decide how many minutes it will take.
Yeah.
Google stay away.
Okay, then you miss. See you later. Bye-bye. I don't give a shit. Okay. Okay. I know already what I'm teaching, so I don't need to know more. It's your job. Okay. Okay, let's go to the next section. The next section is very cool. That's why I wanted to take a break here, but let's continue. So we can take a break somewhere in between. Maybe when your brain is about to explode. Okay. Next section. We can now go to deep neural network. Okay. Slowly, we can start to think about how do we actually build or start to think neural network, and eventually deep neural network. Okay. I will try to cover at least two of the main topics, which is gradient descent, because that was also related with the previous topic. You remember the definition of this loss function, and that we want our gradient to be high when the difference between the true and the prediction is high. Why is that? Then the most important topic of the whole neural network, how does gradient descent actually combines with backpropagation? How do we optimize a neural network? If there is time, I just briefly go over convolution. I guess no time for modern architectures, okay? But you will see those few of the notebooks and examples already on the GitHub page, okay? So for the terminologies, because I will use it, and since if you don't know how I will use it, so usually I break it down into, let's say, 2 or 3 components. So we call the input layer as the layer where we feed the data, okay? So no optimization is ever happening on the input layer, okay? Nothing is going on the input layer. That's just feeding of the data. When I say input layer, that's the data. Nothing, no optimization is going on. Then in between, we have some stacked layers. When I mention hidden layers, that's some layers between input and the output, okay? What are the stackings and etc.? They will be clear soon. Just I'm making sure that the terminologies are understandable. So we have input layer, we have hidden layers, then at the final, we have output. Essentially, that's how we build a deep neural network, okay? Input, you stack some layers. What is the layer? What is a layer? What's happening? We will see. Then finally, we have output, okay? So last year, no, not last year, it's 2026. Time is running too fast. Not last year, last year, 2024, okay? The Physics Nobel Prize was given to Jeff Hinton and John Hoffel, for discovery of the very preliminary neural network, including a perceptron, Boltzmann network, and Hoffel network. Okay, so I checked the image, the press release, and I see this beautiful diagram on the press release of the Nobel page. So we will see another picture later on, but this is a very cool representation of how do we actually give this term neural network. It's because we try to think about building up connections to recognize patterns, okay? So let's say the idea is that, let's say if I see an image of a cat, certain sections of my brain neurons, they get lit up, okay? The idea of the neural network is that I try to build it by hand And hopefully when that network or the computer sees a picture of a cat, certain sections of that network lightens up. When it sees a dog, some other sections of the network lightens up. Usually the way we think is very simple representation. We can compare them side by side. So we have the nucleus here, and then we have the connections in between, the actions. Okay? So you can think of this as something like a mini neural network where I have inputs. Okay, so these are some connections. So if I compare this one with the previous picture, you can think of this as some sort of actions, and these are your neurons. Okay. So for this picture, this is very simple representation of what we already discussed. So what we already discussed is a linear transformation. So you see on the right-hand side, we already have the Wx plus b. So we have the linear equation. And then I have something called an activation function. So we have the linear equation. Then I have an operator function. Okay. I don't know what is this function, but it's operating on this linear transformation. The linear transformation, I can think about this as a series of inputs. Okay. So I have x1, x2, x3. All of this has certain weights, W1, W2, W3. So you can think of this as when I see a picture of a cat, maybe this connection is very much activated. This weight is very much higher than the other one. Okay, that's the way we think about it. You will see later on more. So most of the times, when we go to deep neural nets, we are thinking about complex data, not just some simple linear representation. Okay, complex data. So most of the times, this function will be a nonlinear function. Okay. So let's see through some examples of this function. Usually in the literature, this is called an activation function. This you can think about activating that particular neuron. Maybe it activates this neuron. Okay. You will see later on what exactly it means. Okay. So the most common tool, you know actually already one of them. That's why I discussed the sigmoid function or the logistic regression. It appears naturally. That's why I spent time on that. This is a very common activation function for a neural network. The other one is a tan hyperbolic. So sigmoid function essentially, as I discussed, it squeezes the output from plus minus infinity, 0 and 1. Whether the tan hyperbolic squeezes the output between plus minus 1. Okay. But these were now discarded because the training time takes a lot of time. You end up in the weird spaces in the loss function. The most common one that are usually used these days, some variations of this function. It's called the ReLU. ReLU is very simple. It basically outputs the input whenever the input is greater than 0. So you see here, whenever the input is less than 0, it's basically 0. And then it's just y is equals to x. So it outputs the input whenever x is greater than 0. Okay. Now this one you will see on the class later, the third class, and also for the data processing and etc. This requires scaling of your data. You will see also on the notebook today, if we have time to go, at least 5 minutes. How do we scale the data for images and for other stuffs? You have to keep this in the back of your mind. You just cannot feed your data directly as it is on a neural net. Okay, at least in the beginning training phase from the scratch. Let's now start to think about very simple problem. How do we go from some simple linear decision boundary to some complex ones? How do we think about a deep network? So let's just try to replicate a simple logic gate. Okay, let's say the AND gate. We all know this from our bachelor class, even probably from high school. So let's say the first one is AND gate. So it's basically a direct multiplication of two inputs. So you can think of this as like a data matrix. So you have two features and 4 samples. So you can write it as something like 4 times 2. 4 samples and 2 features. This x1 and x2 are your features. We can also have the, let's say, the other common gate, the OR gate, which is basically the sum of the 2 inputs, binary inputs. Okay, let's now try to see something interesting. So I said that we can take this x1 and x2 as features. So let's try to draw a diagram of x1 and x2 and try to mark this 0 and 1 with some different colors. So let's see, how does that look like? Okay. So what does this mean? So let's say when x1 is 1 and x2 is 0. Where is this? x1 is 1 and x2 is 0. My output is 0. That's why it's marked with the red color. Okay. Let's see another one. If x1 is 1 and x2 is 1, which is basically the diagonal term here, it's marked with green. We can do the same for the OR gate. Okay, so let's take this one. So let's say this one is, so this axis is x2. So x2 is 1. Where is this? x2 is 1, x1 is 0, and I have output is 1. That's why it's marked with green. I think you probably already guessed where this is exactly going. Just by looking at this, I can simply just draw lines to separate this green and the red point. Okay. Just by visually, it's so easy to classify 0 and 1. So if I think of this as, let's say, a classification problem of 0 and 1, just by plotting it, by visually, I can have a linear decision boundary. Okay, so easy. So the neural network should be able to replicate, and it does. It does very well. A simple one-layer network can do it very well. Let's try to see how does it do it. Okay. So we think of this as we discussed. Think of this as, let's say, 2 inputs, x1 and x2, and I have an extra additional bias term. Okay. Then I try to combine this linear combination. I'm not talking anything complicated, not nonlinear, nothing. Just simple linear combination. The inputs are multiplied by the corresponding weight. Then I have this additional extra bias term. So now at this point, I basically have 4 equations. So how do they look like? So let's see, how does those 4 equations look like? So let's say when x1 and x2 is 0, both are 0, okay? So I basically have, so on that slide, what I have is something like wi xi plus b. So let's say when x1 and x2 both are 0, so w1 times 0 plus w2 times 0 plus b. So this point, according to the AND gate, so 0, 0, that is 0, okay? So this is less than or equals to 0, okay? So that's the first equation. And you can have the other ones, just verify they should work, okay? So how do I think about this? First thing first is that I am seeing that I have 3 parameters, W1, W2, that these are the weights for the inputs, and I have a bias. So I have 3 inputs, but I have 4 equations. So I can have many solutions, first thing first. So let's take a solution, because I know. So let's take a solution, okay? So W1 is 1, W2 is also 1, and the bias is minus 1.5. So let's try to verify this, if this actually works. So let's say, which one should we verify? So let's say we go with the last one, okay? So x1 is 1, x2 is 1, and we say w1 is 1, w2 is 1, and my bias is minus 1.5. So let's try to do this. So 1 times 1 plus 1 times 1, w2 times x2, minus 1.5. So I have 2 minus 1.5, 0.5, which is greater than 0. Now I can have a simple threshold cut. Whenever it's greater than 0, that's 1. Look at this. All of these equations are linear equation. That's why we could draw that linear boundary. So cool, okay? Super cool. We didn't need to do anything. This is just a very simple problem to replicate this. We can do the same for the OR gate. Let's not go there because it's similar. Where it doesn't work for something called an XOR gate. So you see the input and the output. Let's try to plot this. So one more time. So we have 4 samples. Let's check the truth table. So we have 4 samples, 1, 2, 3, 4, 2 features. Let's try to plot this. Oh, now they look mixed up, okay? Now it's very difficult to draw one line to separate this red and the green, to separate the class 0 and 1. So this was a paper with almost, I think, 30,000 citations now by Marvin Minsky, one of the most amazing computer scientists. So this was proven that it's impossible to have a single linear decision boundary that can replicate this XOR gate cuts. We cannot have a single decision boundary that could separate this X1 and X2 feature with this green and blue, green and red. Okay, not possible. So how does this work? So let's go back. Let's go back because this is important. For this one, we thought about this. We just take in the input, just make a linear transformation, and then try to find some conditions for the weights. Not possible anymore. We cannot find this W1, some combinations of W1 and W2 that would help us to draw a boundary. But instead of one boundary, what if I have 2 boundaries? Who said that I need to have only one line? I can have 2 lines. Now between these 2 lines, I have the 0. Outside the 2 lines, I have 1. This is the starting point of a deep neural network. This is the starting point of multi-layer perceptron. Initially, I have inputs directly connected to the output with the simple linear transformation. Now, that gave me one decision boundary. I need another decision boundary. I added an extra layer. So you think about problems like this, okay? Whenever I have some complex space where I want to make some cut, you can think about the different layers of neural network trying to create complex decision boundaries. Different layers of network trying to find weird features in the data so that they can make a cut, have reasonable decision boundary. This is the starting point. This is a very famous problem from 1970s. The XOR gate problem of neural net. Not possible with a single layer perceptron. Now we're gonna go to multi-layer perceptron. The mathematics works something like this. So very simple, not this one, very simple. So we have same linear transformation for the input, but now I added this H1 and H2 as in between layer. And then at the finally, I have another linear transformation. So now I think about this H1 and H2, this additional layer that's helping me to create this extra additional line, okay? Now I have this extra 2 lines. Very nice way to think because now we have a building block. I have some linear decision boundary, okay, that works for some simple problem like AND or gate, but a single linear decision boundary doesn't work for XOR gate. So I need more. How can I deliberately have another line? I can just think about adding an extra layer. It does the same linear transformation. Now, can we go back to this picture? So all the time so far, we discussed only, okay, so let's make a cut here. So this one was the one, yes. So we had something like this. All the time we discussed only linear decision boundary because they're so easy to think because the transformation is very simple. It's just y equals to mx plus c. But we can have a non-linear cut, something like, let's say, I don't know, something like this. Who said this doesn't work? This works also. For that one, instead of a linear transformation or a simple activation, I can have some complex activation, something like, let's say, I can add ReLU as my activation instead of just a simple linear activation. Where was ReLU? Back, long time back, ReLU. Or I can add a sigmoid and you can have complex decision boundary, okay? Non-linear decision boundary. We started from linear, that was just to visualize that single layer perceptron not good enough for a complex problem. We need a hidden layer, okay? Then That hidden layer was basically doing the same linear transformation. Okay, instead of linear transformation, we can also do non-linear transformation. These are the building blocks to start to think about neural net. Comes the very important theorem. Never forget, because we started the whole class, the whole machine learning was kind of dedicated to think about your problem, making this problem as like a optimization problem. That actually stems from this universal approximation theorem written by two amazing scientists, mathematically proven many times again and again. This paper now has 40K citations almost. The idea of this paper is that, so let's say the network that we built, we had X1 and X2 as input, and then we had one hidden layer. So I had only one hidden layer. The theorem is saying that I can have as many neurons as possible, okay? Here I had only two, I can have as many neurons as possible. And I should be able to replicate all sorts of training data with a certain degree of accuracy, okay? Neural network acts as a universal approximator for any kind of problem. Super cool. So here, an automatic question arises, okay, so this looks a very wide network. But wait, but when we started the class, just the background of this slide, but I have stacked up layer, okay? Why not go like this, but stack like this? So this was another common question. Whether should we go wider or deeper, okay? Then there's a big meme from Inception, because this is also related with a very common neural network architecture. That's called Inception, because the scientists were motivated by the movie. That's why the meme came, okay? So we think about building not wider network, but deeper network. And the way to think about this is, let's say we go back to this one. We stack up layers. We're basically thinking about making many cuts. So let's say I have a very complex data set. I don't know, something very complex, like completely mixed up in 2D space. Of course, 2D is very simple, but I will have, let's say, n-dimensional data space, and I have very complex thing. I can have very complex decision boundaries. Okay? Very complex decision boundaries. And I can think about this, each of these complex decision boundaries as some form of features that are given or provided by the layers. So the deeper we go, probably we are expecting to capture more hidden features in the data that are not easily available at the first one or two layers. Okay, I think we can stop here, right? Is it 240? I think the brain is about to explode. So I think we stop. Well, so let's see. But let's see. Wait. Maybe the next slide is too easy. Okay. Oh, the next slide is too easy. No. We cannot stop. We can no, because when we come back, we have to go like a very hard thing. Okay. We cannot come with some easy slide. Let's finish the easy one. Let's share back. Okay, so that's the motivation for going from one layer network to deep neural net, and then to think about nonlinear activation. Because most of the time we will deal with nonlinear problems. Okay, something like, let's say, image recognition, something like, let's say, time series anomaly detection, something like, let's say, predicting new molecules or something like that. Very, very complicated problems. Okay, so we established that we need, at least we can think of just from the first principles, that we need deeper network with maybe some nonlinear activations. Okay. There's another way to think about this. We can continue and build on the same principle again. So possible idea of thinking about, let's say, going through the data and apply the neural network is that the idea of the applying neural network is that this thing, this black box, it's usually all, a lot of the times you will see in classes, other classes, if you follow some other lectures, it's most of the times it's represented as like a black box, okay? So I have X and it produces Y. This is a black box, okay? This is essentially back to this universal approximation theorem. This is like a function approximator, a complex function approximator. Another way to think about this would be is to finding patterns in the data. So let's see, images are the best way to think about this. So let's see some images. So let's say I have given this handwritten data. So these were some high school handwritten data, modified and made public. Initially released as NIST, now it's MNIST. Probably you have 1 million citation with this data set because this is so easy and so heavily used to understand or go through building deep neural network and understanding this. So let's say 4 different people write 4 different ways of zero and blah, 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 blah. But how amazing the brain is that we don't even need to think. This 7 and this 7 looks drastically different, but we would immediately recognize, okay? Now, you might think that, okay, let's say we start from this 3 and we have these other 3 examples from other 3 people. We can maybe just overlay each one of them on top of the other, and then maybe we can just find the difference. So let's say I overlay this 3 on top of this one. So I have some pixel differences, okay? But this alone is not good enough because if I shift this 3 or overlay this 3 on top of this one, I will have some other different pixels that are lighting up. So only the pixel difference is not good enough. So I need to think about finding some generalized pattern in the data. One of the most famous computer scientists, Herbert Simon, had this very famous quote that the more relevant patterns that you have at your disposal, the better your decision making will be. I think he mentioned this comment as like a political election for the American president. So think about how politicians make decisions and you will find some patterns and then make a decision, okay? Other way also we can think about, let's say, not only this features in the data, but we can also think about that there's different layers trying to find different features. So let's say we can break this 9 down into a circle and then to 1. So let's say 0 and 1. We can break this down 8 into 2 different zeros appearing at 2 different sections of the images. Another way of thinking about pattern in the data. So this is my cat. I guess all of you have seen this, okay? It's good to catch him in the goofy position like this, okay? It's a very rare moment. Okay? So now it's very common. So I can, let's say, build the image recognition and put it on my door. So when it goes out, it comes back. It's a simple Raspberry Pi. But this doesn't work anymore because now there is another stray cat that started to come in the home. So I have to remove this, okay? So he comes in. But look at this. This is so cool. So the reason I had that this camera on the door is because there's another black cat, okay? But there is another stray tabby cat like this. But whenever I see them side by side, I immediately know which one is which. But it's so difficult for a computer to understand, even just to recognize that these two are same breed, same animal, okay? Cat, okay? Brain is amazing. Think about this again and again. Next time when you go out, take pictures, think about these things, okay? Super cool. How do we build a machine that basically replicates our vision? And you can think about, well, I love taking pictures, no? And we work with astrophysics data, so it's mostly images. But you can think about any type of data. Let's say gene sequence or a time series or your molecule structure. Super cool. When you see a structure of molecule, you immediately know. I remember my chemist friends, organic chemistry. Oh my God, they were so cool. How do you recognize? Well, it just happens. Okay, so brain is amazing. Now, another point that we mentioned again and again is that we better think of our data as some form of matrix. So let's say we discuss the tabulated data as a matrix. So we had this X1 and X2, this as a matrix. We can also think about, let's say, a time series. So let's say you join a bank and then you have to predict the stock market. Okay, so let's say S&P is now 3294, tomorrow is 3298, blah 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 blah, and then you have to predict. So this is like a time series. Okay, so you have to predict what's the forecast in the next 10 days. This is a 1D data, but we can also think of this as a 1D matrix. This is a tabulated data. I can think of this as a 2D matrix. Your molecule. So you have different molecules placed at different positions. You can think of both as 2D or 3D data structure, whichever way you represent, but better to think about this as a matrix. For the Pythonic way, we have different ways, no? List, dictionary, tuples, arrays. We're going to stick with arrays. 1D array, 2D array, 3D array, blah, blah, blah. Okay? Okay. So for images, let's try to think about them as some form of 2D or 3D array. So let's say I have this very simple smiley picture. Okay? It's just a simple 2D array, and I have only 0 and 1. So I can put those values on the pixels. You see, this now replicates exactly like a matrix with 0 and 1. Very cool to think like this. Then let's say I can go to from here. Okay, from here I can go to, let's say, a grayscale image. Grayscale image can have continuous values between 0 to 255. 0 is black, 255 is completely white. I can also have that as a matrix, another 2D matrix. Okay. Okay. Usually when you go to, let's say, write the program, you usually think about this as a 2D structure. So most of the times, this array will be given as this width, height, and this 1 essentially represents the number of channels. So for a binary or grayscale image, we have only 1 channel. So let's say you take a picture with your iPhone and then you apply the black and white filter. Basically, you have gone from 3 channels, RGB, red, green, and blue, to only 1 channel. Okay. So let's say now I have this 3 channel image, like a house with a sun. Okay, just a simple image. I can also think about this as a matrix. I go channel by channel. So let's say I go to green channel. Of course, the green pixels will have maximal value. So about 200, reaching to 255 or something. Red channel, of course, the green pixel will have 0 values. Blue channel, little less value. Okay? The white pixels are always maximal. So all channels provide equal number of contribution, 255. The black channel is basically absence of intensity. So that pixel is 0. Okay. Now, if I put those numbers, they look like 3 different matrices for red, blue, and green channel. The way we usually think about this data, we try to stack them on top of each other. Okay, so on the top we have red channel, green, and blue channel. So what exactly happened if you write a code? So we have W width, height, and channel. So we have, let's say, this represents the red channel matrix. Then we have the same for the blue channel. And then we can stack them on top of each other. This then would look like R and B image. Okay. Or here we have 3 channels, so this should be C. Okay. I say 2 channels, because a very common thing in, let's say, for physicists to apply for jobs in, let's say, for medical imaging company, especially high energy physicists, to join as a image researcher or computer vision researcher for medical image analysis. So you have this MRI images, which can have many channels, 10 channels, or maybe 5 channels. So it's not only limited to 1 or 2 or 3, okay? It could be any numbers. But you can apply the same principles. We have taken some amount of photons, then we are binning the photons according to the energy. So here we bin the photons into R bin, red bin, we call this, and this is blue bin, okay? You can have many other channels. You can think about them as energies. So that goes for this MRI data. Think about many different ways, whatever way you want to think. Let's take a break. The second part is complicated, little complicated. How do we think about gradient descent and backpropagation? When do we meet? I think we can meet at 2:48. Let's see what the students do, and we can meet at 3:10, 20 minutes, 22 minutes. We'll see.
Shubha,
Yeah,
can you
go.
No, sorry, this is not about the lecture. I just want to say, I made you host. I will need to step back for 15, 20 minutes, but please don't close your Zoom because now you're the host.
No. Sure.
Not to lose it. Okay. Okay. Okay, so 3:15, 3:10, no meeting, and you will see in which room you will continue, either amphitheater or computer.
Yes,
Right?
yes,
Okay.
yes.
Okay, nice. Marta is asking, Shubha, when does the class finish? So probably around 4, right? Shubha? Shubha, did you hear me?
Should be the maximum 4 or 5. Yeah, maybe 5 minutes more. I don't know. Yeah, but close to 4. Yeah.
Close to 4. Okay, good.
let's begin. Okay, so I guess at this point you probably get accustomed with the with the notebook and where exactly you can run it super simple without making any changes to your computer. So let's say if you go to the web page and let's say we go on this one because this is the one that we're discussing. So let's see if I click on this, that will take you to a GitHub page, and I think you don't see it there, right? Do you see the download button at the end? When you press the download button, you can download it, okay? I will come back to this notebook. You download the notebook and then you put it on your Google Drive. Go to the Google Drive, make a right click, go with open the notebook with Google Collaboratory. So what is Google Collaboratory? Did you see it? Okay. So it will not show up naturally. So you have to go more options and blah, blah, blah. But it looks something like this. You remember the icon? That's the CEO for the Collaboratory. So you're going to go right click and open with Google Collaboratory, then it will open and then you could just run it. Okay. So I guess a lot of other people will also use this. So it's better you get accustomed with this. Okay, so let's get back to the slides. Okay. Okay, so we essentially set up thinking about the deep neural net, especially going beyond one layer. And then we also thought about data and data structures, thinking about data as some form of either 1D, 2D, or 3D matrix. Now, we want to think how we can actually train this deep neural net. What are the main principles that goes behind training the deep neural net? So the two main algorithms, gradient descent and backpropagation, they are very correlated with each other. So first, let's go through the gradient descent because that is way more common. So let's say I'm given this handwritten data, okay? So now the idea is that after it passes through the network, remember how we thought about this white dots or the circles? We thought about them as some form of neurons. And these neurons are connected with each other. Every neuron is connected to other in the corresponding layer, okay? So it passes through, and the idea is that if I have at the end some number predictor, like between 0 to 9, because my images are between 0 to 9, hopefully this number 4 lightens up because I have given an input image of 4. Okay, so now at the very top, what you see here, 784. This one is fixed, but not the in-between numbers. So what is this 784? So let's go back to this one. Stop share. Yeah, I can share this. So you can download the data with only one line, okay? The data is already inbuilt within the library. You don't need to install anything. If you run it on the Google Cloud, Google Drive, you don't need to install anything extra. So you download the data, and then you see that the data looks something like this. 60,000, 28 times 28. So the 60,000 is the number of samples. And then I have the height and the width, okay? So this is a common way to have data presented. First number is the number of samples. Then for images, it's height and width, and we could have number of channels. In this case, the channel is 1 because it's just a binary image, another grayscale image. And then I see that, you see that the train y dot shape, y is the label. You remember how we thought about this? So we have x and y. X is input and y is output. And this is supervised learning. So for every x, I know every y. So for every 60,000 samples, I have a corresponding label. Okay? That's why no other number, because this is just only a single number. then you can actually visualize. So let's say what I did is, let's say I randomly select the image index, and then I just try to tabulate. How does this look like? It's very difficult to make a guess just by looking at it. It looks like a diagonal line, so you can probably make a guess, okay, maybe this looks like a 7. Okay. Then you try to check what is the true level of this thing. It's actually a 1. So it's not a 7, even though it looks like a 7. So what about that 784? That 784 actually comes from something called flattening the array. You will see it later on. So we have 28 by 28. That's the height and the width of the image. 28 by 28. Instead of having this fed to the neural network as a 2D image, we feed it as a 1D array, 784. That's why that number is fixed. I will come back to this one more time, just so that you are not confused. What is that 784? And why it's written only for that layer and none other else? Because that one is fixed by the data. I cannot change it, okay? Because my image is 28 by 28. So when I flatten it, it's already 784. In between, I can have 10, 15, 20, 30. Those are number of neurons, okay? So you have to test many numbers. These are called hyperparameter checks in the neural net. What sort of configuration gives you the best result? Okay, let's try to think what about the optimization? So the network that you have on that notebook essentially has about, I think, 20,000 or 30,000 parameters. So think about this. We went from linear regression, like one parameter, basically modifying the weight. Then we went to multivariate problem, let's say 4 or 5 features or maybe 20 features. Now, our network has about 30,000 parameters. So now we are trying to optimize over a lot of the parameters, a lot. Okay? This is a very small network. This is very, very small network. Let's say, to give an example, GPT 4.5, I think, has about 6.7, about 7 billion parameters, okay? So this is only 30,000 parameters. Okay. So one more time, for every X, for every input, I know Y. So I know exactly what I'm comparing with, okay? Supervised learning. Okay, let's see. How do I think about this? So this one basically describes what I just told you. It's flattening the array. It's very simple. If you are not familiar with Python, it's just a one-line code. So let's say I have this 2D array, okay? So 2, 3, 4, 5, 6, 7, okay? It's, let's say, a 2 by 3 image, okay? So 2 by 3. Instead of 28 by 28, I have 2 by 3 image. So if I flatten it, this should be a 1D array with 6 inputs. It's very simple. I just reshape the array. Python is so simple. I mean, these comments are like so intuitive to understand. I took the first shape, which is 2, the second shape, 3, and then I apply reshape. It's just 1D array. So I can do the same for the image data. Reshape, height and width, and then I have 784. That's how I flatten the array. Okay. How do I now go and think about this optimization? So for the network, the zeroth layer, the input layer, okay? The zeroth layer is the input layer. No optimization is going on there because that's the data going in the network. That's the input layer. Optimization starts from the second layer. Now the second layer has many neurons, 10, 15, 20, I don't know how many I took, maybe 16, 20, I don't know. But let's just focus on only one of them. For this type of network, every input is connected to every other node. So let's say I have 2 input, and here I have a layer with 3 neurons. So each of them will be connected to each other, okay? So this type of network is called a fully connected network. I just focus on only one. Let's just focus on only one so that we can understand what is actually going on. So at the input layer, I have 784 numbers. This operation, you remember that this operation is always linear. The initial operation is always, in the literature, it's called affine transformation, just a linear transformation. Let's just go back. Where was it? So yeah, something like this. I think we had a very nice function approximator diagram. This one, yeah. So first operation is always linear. Then I can keep it as linear. We discuss some linear decision boundary problem, but also we can think about complex problems and apply a non-linear function, something like a sigmoid function. So that was what was shown on that slide. So let's go to that slide. So first I have linear transformation of the input, and then I applied a non-linear transformation. That's what I called an activation function. Okay, let's see one more time. Okay. So this W, basically the weight of the connection. Okay, that's how exactly it was in the previous diagram. The A1, A2, AN, this case, this A1, A2, AN are basically the input numbers. Okay. At the zeroth layer, these are just the data. When I go from the other ones, they should be called activation. So weight, basically the connection of the neurons. A are the activation. At the zeroth layer, this A are just the inputs. You remember we have 784 numbers. 784 numbers, so we have 784 weights. Okay. In the next layer, it will change. I have, let's say, 16 neurons, so it will have 16 weights. Okay. So I'm focusing on only on one. Oh, yes. Go to input data. Yes. Yes. So we started off with an image that has 28 by 28 size. I just flattened it, 784. That's right. That's right. That's right. Exactly. Exactly. By the way, this is not so many because 28 by 28. Yeah. Yeah. Yes. 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 Exactly. So let's say if you take a tabulated data, it's insane difficult to find data with 784 features. Good luck finding. Okay. You will not find the problem. Okay. But it happens for images and maybe some other types of data. Okay. No, 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 no. We are just trying to establish. In this one, also, let's say we have 10 or 15. I'm just focusing on only one. So that what function is going on through that node, just to focus, okay? We have many, so others are connected to other nodes. Like here, and I'm focusing, let's say, only on this one, okay? So initially, when we start the network or start the training, the weights on these connections, they're randomly initialized. Okay, between some numbers, it depends actually how you initialize. Some numbers between -1 to +1 or between 0 and 1. You can actually very specifically give this instruction to the network, whether it will be between 0 and 1 or -1 to 1. So you initialize and these weights are random at this point. So you can understand that the prediction would be very terrible. So at the first training, when the weights are randomly initialized, the prediction is terrible. And the difference between the input and the output at this point is very high. So let's say my input is an image, the level 4, but the network predicts that it's a 9. Okay, makes no sense. So the idea here is that the difference is very high. That means the loss or the cost function should be also very high. What do we think about the loss minimization? Think about this as basically trying to make the gradient of this loss to 0. That's just a simple optimization idea. So now for a convex problem, something like, let's say, linear regression, I have a very nice, well-behaved function where I have a simple, predefined, nice, mathematically calculated global minimum. This will not happen for complicated problem like molecule generation, image classification, time series anomaly detection. It will not happen. Complex data, okay? And complex problem. So we will not find problem like a global minimum. So now, how do we think about this? So our network, let's say, have about this 25,000 parameters. So we are essentially trying to optimize this 25,000 weights, or let's say 30,000 weights. So we have to nudge these weights up, down, less, however you think. So basically making it big or small so that the difference between the input and output goes down. So that's the idea of the training. I start training randomly, prediction is terrible, then the network gets some information that the prediction is terrible. And the idea is that now somehow I have to update this weight parameters so this difference gets reduced. Okay. How do I do this? This is gradient descent algorithm. This, one more time, neural network will not lead you to a global minimum because it's a non-convex problem. It will not happen, okay? You're gonna end up something like within the local minimum, somewhere, okay? But how does it work? So let's say for this problem, this local minima is good enough, okay? I have 98% accuracy. So how do I get to there? So first thing first is that when I start the random initialization, within that cost function, by the way, this cost function is super simple. It's just for visualization, right? Because it's shown only in 1D. We have 25,000 parameters, which is not easy to visualize. This is just for visualization purpose. We're going to start with some random position, right? So let's say we start from this position. So first thing first is I have to tell which direction to go. Whether should I go to left or to the right? That depends on the slope of the curve at that point. If the slope is positive, so this is positive slope, the other one is the negative slope. Okay, so that's basically drawing lines. Positive slope, negative slope. Okay, if the slope is positive, I go to the left. If the slope is negative, I go to the right. So we are calculating the derivative of the cost with respect to weights. This is being done for 25,000 weights. Okay, so this is happening simultaneously. The network has started to train. Okay, so now from the slope, I can make a decision on the direction. Okay, so I have made a direction. I have made a decision on the direction. But how much should I move? How do I make that decision? So I have made a decision on the direction, but how much should I move? Because that's very important. So let's say, so the curve that's given is looks something like this. So let's say I'm here and I made a huge step. I end up here. That's not good because then I have to keep on training before it falls back down here again. But maybe if I take small steps, maybe I can lie somewhere down. Okay. So how do I make this decision on the step size? That also turned out to be very simple for gradient descent. Okay. This is actually proportional to the slope itself. So let's see what it is. So let's say we randomly started at that point. I calculate the slope. I calculate the slope. Okay. The step size is proportional to the slope, the magnitude of the slope at that point. Okay. So let's say when we are far away from the minimum, the slope is very high. So far away from minimum, somewhere here, the cost is high. The cost is minimum here. The slope is very high. I can take a big step. Here, the slope is small. I take a small step. Very simple. Very simple. Only two-step process that's happening within gradient descent. First is the decision on the direction, then the decision on the step size. The direction is given by the slope direction. Step size is given by the slope value itself. Now I can keep on updating this for this 25,000 parameter. So the network will train, I don't know, for let's say 100 steps. Then I can reach hopefully close to one of this local minimum. Okay. The idea is that once we reach close to the minimum, we don't want to overshoot. Otherwise, the training will continue forever. Okay. It will jump and bounce around. Not good. When we are getting close to the low value of the loss, we try to take small steps basically telling the network that, hey, you are close to the solution, make proper decision. Take more time, make proper decision. Okay? So you can see here on the GIF on the right. So when it's close, the step size is very, 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 very small. Okay. When it's high, the step size is long. Okay, so that's the gradient descent algorithm. That's how you're updating the parameters. So how does this relate to the back propagation? What is now back propagation? Okay. One more thing is that think about this gradient descent as two-step process, right? So we have the direction and we have the magnitude of the slope. So this, you remember from the linear regression, we already discussed this as like a gradient vector. Okay, so I call this cost and not loss, rather L, because later on I have a notation for layer L. So I call this cost. So now you can see, so I have this 25,000 cost, okay? So I have many costs. These are corresponding to the corresponding weights, W0, W1, W2, till W25K. And I could actually check if the number is small, that means update the weight small, and then I have plus and minus on which direction I'm telling the weight to move, okay? So both information are actually encoded within the gradient itself. So random initialization, bad result. Now I am trying to tell the network what exactly to do. That thing is gradient descent, trying to optimize the weights, okay? The way it's usually done efficiently with something called the back propagation. Come next. On the literature, you will find this this very nice mathematical equation for gradient descent. I wrote this explicitly because don't get confused with this to the power of k. This k actually denotes the iteration step. So this k is the iteration step. Okay. So this is kth step. So let's say I'm training the network. At the first step, it's very terrible. Then I go 20th step. So let's say this is the weight value at the 20th step. This is the gradient of the weights at the 20th step. And then based on that, I update the 24th step. Okay, so this K are the iteration step, because this is happening over many iterations, many steps. Okay. Now, back propagation. So we understand gradient descent. What are the two main things of gradient descent? Magnitude and direction. We figured that out. How do we actually propagate this information? What does it mean, propagate? Because I have to update these weights. I have found some big difference between the input and output. I have to update the weights. I set up the rule of update. How do I pass this information to the weights? So let's see. So let's say back to that same network, fully connected, all neurons are connected to all. So here, let's say I have 16 and 10 or whatever, 16 and 20. And then at the final layer, I have the exact number of outputs I want to predict. In this case, it's between 0 and 9, so basically 10 outputs. So what I want, given 2, I want that neuron, final output layer neuron, to lighten up, okay? So now I see that this number is very small. When I give 2 at the initial stage, it predicted 3. So the idea here is that I want to reduce the output for 3, but I want to increase the output for 2. The same thing should happen otherwise, okay? I want to fine-tune this output 2 so that it's now maximum out of all the numbers. How do I pass this message? I have a big loss. I have 2 on the input. I predicted something like, let's say, 3 or 6 at the beginning. Okay, good. So the idea here is that I have to now pass this message backwards because I got this output on the final layer. So I got the output on the final layer. Now, based on this, I have to pass the message what's happening here. And that's usually connected via these weights. And these are the activations. So keep this in mind. I predict the output. I have a loss. Now I have to pass it back. Okay, so let's see. How does it work? So now I focus only the one neuron that's trying to predict this 2. So it's at 0.2. So now I have 3 different options. If I look at that expression, I can increase the weights. So that means the connections that connect to 2, I can increase the weight so that this number go up. But I can also increase the corresponding activation for the 2. Okay? So let's go back one more time because this is a source of confusion. So at the input layer, when I say activation, these are just data. For in-between layers, activations are actually network activation, okay? This is calculated from the previous layer. So here, these are actually activations, okay? So activation, you can think of some number. If it is high, that means that neuron is activated. If it is low, that neuron is not so activated. So we have 2 different options. We can increase both. We can increase either weight and activation. This is 1 from the linear equation. We have finally also the bias. We can also actually increase the bias. So we focus on the weight and the activation because the linear transformation is very much dependent on those 2 parameters. So if you remember how we started the linear regression, we had something like y wx plus b. Look at that. The x back in linear regression was the input data. Now the x is a0. That is input to this particular section. Okay, that's how you can think. When I'm thinking about input layer, that a will become x, the input data. Any in-between layer, that's just the activation. Then you can always draw parallel. That's why we spend so much time setting up the logic. So now the notations. So get accustomed with these notations. I will not go on the math because the math is exactly same as the logistic regression, but the notation is very confusing. So let's clear this up because that's how it's usually written in the paper. Oh, that's how it's usually written in the paper. So what happened? Cannot see. Yo, this is okay. Hide the control. I cannot hide control. What is this? No, not this. Oh my God. Ah, this one. Okay. Okay. So when I'm focusing on a particular section of the network, you think about the activation coming from the previous layer. So that's why it's written with L-1. That are these neurons. The corresponding WL is the weight of particularly that layer. Then I have the final activation. In this case, it's just the output. You can think about in-between network. So I had input data. So this is my input layer. Then I have H1, some neurons in between. Then I had H2, let's say another hidden layer, some neurons in between. And then I have output, okay? So I have 0 to 9. So at the input stage, the activation is your input data. One more time. Now for the final layer, that's actually the output. So when I'm denoting this, remember that this AL-1 represents the layer before. So if I'm thinking about this, there is no concept of activation because the data starts from here. If I'm thinking about this, the activation is actually the input data. If I'm thinking about this layer, the activation is whatever has happened here. If I'm thinking about this layer, that's the output. This is AL. The activation is coming from here. Okay? So the way it's usually written, even though the math is like, the notation is like weird, we are back again. Look at this. We are back again with the same linear transformation. That's why we spend so much time on linear regression. Linear transformation, affine transformation, and then some nonlinear function on top of it. Okay, that's the activation function. So look at this. I'm trying to predict ZL. That's this, related to the final layer. In this case, it's the final layer. That depends on the weight of this layer. That's WL. That WL is connected to AL-1. Okay? That's it. And of course, I have the bias for the corresponding layer. That's it. Look at this. This is exactly a linear transformation. And then on top of this, I apply the sigmoid. Okay. So that's how the messages are actually passed through. So I have the activation. Okay. I see what is the activation. Okay. I have to nudge the activation up or down. The activation gets passed through to ZL. ZL then passes the information to weight and the previous layer activation. How cool is that? Back to linear regression problem, but thinking about in a different way. Message passing from bottom up. Super cool. Okay, we'll never forget if we remember it like this, like a stacked layer, final output. I want to modify this. How is this connected? This is connected to ZL, which is basically affine transformation. How is this affine transformation connected? It's connected with the weight and the corresponding activation. I want to modify AL. That means I need to modify ZL. ZL is connected to others. But that's another way to think about chain rule. Okay, we will see on the next slide. Yeah, so final activation, I compare it to the true label Y, and then that basically gives me the cost function. Okay, look at this cost function. Instead of Y hat and Y, I have AL, because now AL is my Y hat, the output. Now the chain rule makes even more sense. How do I think about the chain rule? Because let's say I'm trying to make a derivative of this cost function with respect to the W. So d cost over dw. I will never forget if I remember it like this. C is related to Y hat or AL. AL is related to ZL. ZL is related via this with the linear transformation. That's it. Okay. So now you can go back again to the logistic regression chain rule. Think like that. That's why we spend so much time on linear regression and logistic regression, so that we have a very reasonably strong base so that we could understand this. That's how backpropagation works. It's a message passing from the final layer to the layer before. This is a big research area of neural net, because as the network gets deeper and deeper, this message passing gets very, very complicated. Okay? So this is a big area of neural net, but that's how it works. We have a great meme. So the physicists and mathematicians have a very strong advantage of really to go into deep neural net. That's why it's better that we spend time. No? So this Shiba Inu, this superpower Shiba Inu is saying that I studied linear algebra, matrix, blah, blah. I understand almost everything. But then, no, you study just from the deep learning, and then you don't even know the chain rule properly. Then it's not good. Okay, but we can start at some point. And it's, if we remember the visualization, we probably will never forget. How is chain rule related to this message passing algorithm? Something like this. We're passing the message from the bottom up. That's how exactly the chain rule is constructed. Okay, that's it. We are done with backpropagation. We basically optimize it like that. You look at that expression, exactly same as logistic regression, exactly same. So no need to go through the math. You can just try one more time. Final summary before check some modern architectures. Okay. So essentially, we have set up a system first to think about a deep neural net. So we started from thinking about plotting some linear decision boundary to go to some more complex problems. Okay. So we think about this always. Remember this one. So given some X, I want to predict Y. I have a black box in between. And that black box is a function approximator. That's how we will always think about supervised learning. Essentially, everything becomes function optimization problem. This for complex problems, for non-convex scenario, these are always done by neural net. If you have some problems like this, I can guarantee you will reach better solution with a deep neural net. You can immediately try. Okay? When you have not mathematically clean convex solution, you can definitely try just simple stacking up some layers and try a deep neural net, and it should reach very nice results. Okay, then building blocks, never forget, because that's where we spend most time. Affine transformation, basically linear transformation. Then on top of this, I applied activation. Activation For simple decision boundary, linear, I can have just the same function, basically linear transformation, basically multiply by 1, because the affine transformation is already linear. If it is complex, like let's say some image recognition or something, then I can have complex activation function. It could be ReLU, rectified linear unit, sigmoid function, blah, blah, whatever. Okay, we can try many different things. Train the network iteratively over several steps. In a research paper, it's usually called an epoch. Basically, your number of training steps, and then weights are updated via backpropagation. I mean, everything. I mean, I write only weights, but of course, weights are connected to activation. Activation are basically, you can think of the first layer is the input data. Okay? Okay, now we can take a break. You basically now hopefully have established the framework to understand the logic of neural network. How do we go from 1 to 2-layer network? If we understand the logic for 2-layer network, then we can think about how do we set up the cost function for the given problem. For that, we spend too much time on regression and classification. Those are the only two problems you're going to see on supervised learning, regression or classification. So you have an idea about the cost function. And then at this point, you can think about optimization. So now all the problem boils down to optimization. How do we optimize? We have algorithms like gradient descent and backpropagation. That's it. That's all the summary. Now there is one trouble. Just end with this, because this is a very important concept. It's called convolution. So when we go to that network, so let's say if I go to that network, can I share? Okay, let me finish the slide, then you will see. So the network that you find on the website, let's say it has about 25,000 parameters. So our image size is 28 by 28. And let's say I have 32 nodes. So this is what I mean. So let's say I have 32 nodes in the first hidden layer. So I have 784 input numbers connected to 32 nodes, plus biases for 32. Not this is already about 25,000 parameters. Okay. This image is insanely simple. You can go to some relatively large size, 100 by 100. And at that point, we can teach about a million parameters. Million parameters with only 32 or 64 neuron layers. Only on the first layer. And what we established is that it's better to build a deeper network. So this is a big trouble. So this is usually called problem with the number of parameters. It's the parameters grow exponentially for a dense network. It's okay now? Wait. Okay, let's pause okay. Because we are done at the end of the class. So how do we actually think about this? What we did is some form of artifacts. It's like we had an image, and then we try to flatten the array. So we go from 2D data to a 1D data. Okay. But we can actually take the images as the way they are. This is usually done via a process called convolution. Okay. So the way we think about convolution, if you look at this expression, don't need to remember this expression. I mean, you should be able to remember it after seeing the visualization. So remember the visualization. Convolution, you think about, let's say, convolving one function with another. So let's say I'm trying to convolve these two functions, f and g. So let's look at this function. I have f with the blue and g with the red. Then, first thing first, what I do is I take a mirror image. So from gt, I go to g of minus t. So that's a reflection about the y-axis. We discussed this with the matrix transformation. I go to g of minus t. Then I shifted this by t minus tau. So now I have shifted this, t minus tau. And from that point onwards, I do convolve these two functions. So I slide this function over the other one. What does it mean? Slide is just a simple dot product at every of those values. Since both of these are continuous, I think of this as an integral. Okay? If they are discrete, they would be just summation. How does that work? So let's say I have this 1, 2, 3, and 4, 4, 5, 6 convolve. So first I flip 4, 5, 6 to 6, 5, 4. That was this mirror image. So I have 6, 5, 4. And then I shift the 6, 5, 4 to the end of this one. Then I slide it over. This is very easy to understand. And if you remember this, you'd forever remember that what exactly happened with this F and G. You never need to remember the formula of the convolution. F, it's usually written with a star, G. So if I'm convolving with the G, so G first gets reflected, then G gets shifted. Then I just do a simple dot product, okay? That's it. Never forget. Okay? But why does this so good for images? By the way, this you can do with one line in Python. So this is just np numpy.convolve. Okay. 1, 2, 3, 4, 5, 6, and you basically can reproduce that convolved array. Why is it so cool? For image recognition, we do the same. Instead of 1D array, now we put the images as images, and then we slide over a matrix, which is essentially convolving. We have these matrices. You see this -1, 0, 1. We slide it over the image. That's called convolution. This is just simple dot product of matrices. Back again to linear transformation. Dot product is again linear transformation. This weight matrices for the images, they will be updated. Okay. So instead of updating this connecting neurons in between, I'm updating a matrix. Number of operations are way less because it's only focusing on those regions, 3 by 3 regions. Those filters are 3 by 3. Those small matrices are called filters. Okay. And I can think about those filters as some sort of detectors. So that's the idea for image recognition. For other tasks also, you can have many different filters and they do different things for your different types of data. So let's say this one, H, Sobel filter, it's a horizontal filter. It will detect the horizontal edges, okay? Let's compare this with the vertical edge detector. This one selects the vertical ones and so many, etc., etc. The idea is that over deeper networks, the neural net will eventually be able to recover the simple matrices like this and more complex. The neural network should automatically recover these types of matrices. It has been proven, it has been shown. And even complicated deeper features. Okay, so we remember this convolution, not the CNN. Okay? Convolutional neural net is the convolution operation done on the images or your data. And that's how we write. Instead of now nodes, we have a stack of feature maps, basically matrices, linear operation again. Now we have output. You're gonna see this at the notebook. I put it on the notebook so you can run it the same. So you can also extract the features from the net. So let's say I have some cat. The idea is that at the initial layers, I'm gonna detect some easy features, but when I go deeper and deeper, I detect more complicated features. Okay. Then there are some modern architectures. I think we can finish it here. Let's just for 2 minutes. Let's just check that notebook for one more time. Just for some of the things, especially with the parameter. Okay. So let's see through this. So let's say, see here. So I define this hidden units as 32 and 16. Those are basically the neurons. And yes. Does it work? No. Wait. One more. Okay. So then we build up a simple neural net. Remember that the first layer already has about 25,000 parameters just from that multiplication, because every node is connected to every other one. You can see how the parameters, the number of parameters are actually obtained, blah, blah, blah. Then you build up the network, the dense layer. The first layer is your input. You have two other layers. That's it. Then you try to predict. You remember during the multi-class classification, these different types of movies, I mentioned that your data is something like one hot encoded. So that's how it would look like. Okay, so your data is one hot encoded. You give an image, and let's say this image is 0, 1, 2. So the flag 2 has been risen up to 1. So that's the one hot encoding. Every other are 0. And then you carry on and build a network and train. Try the same with the convolution. And next, I will come back at the very end with some extremely advanced topics. But hopefully you have a reasonable foundation now to build on it. Be kind to the other lecturers. There'll be some amazing other lectures too. Very cool topics. And since things are changing very fast, almost exponentially, a lot could change in between 2 months, okay? So have fun. Thank you, everybody. I think we can finish. Any questions online? If not, just disconnect. Thank you. Thank you. Okay. Ciao. See you, everybody. Have a nice week.